Hi everyone, we just started studying compact linear transformations between Banach spaces. So at this point, beyond the definition, we don't really have anything at hand. And what's the definition? Well, a bounded linear transformation between two Banach spaces, x and y, say, is compact if the guy maps bounded sets in X to sequentially compact ones in capital Y. Equivalently, if the closed image of the unit ball in X space is compact. All right. Now the first statement that we will discuss now, that is to say that we will prove, is the theorem displayed here, the basic, algebraic properties about compact linear transformation. So if you have three Banach spaces here, then the first one, that's a statement I already explained why this is true in the last video. If you have one of finite rank, so the finite rank linear transformations are those for which the range is finite dimensional. If you have one of those, then that thing is compact. Number two, that's important, it is a norm-closed subspace. That is to say, if you have a sequence in com x, y, which is convergent, then because it is norm-closed, then the limit automatically has to be compact. Number three and number four, these are the ideal characters. So if you take something compact and compose it either from the left or the right with something bounded, linear, then that composition is again going to be compact. And then the fifth statement, sometimes formulated as a theorem by itself, called Schauder's theorem, is the compactness of T happens if and only if the dual transformation of T is compact between the indicated dual spaces. Alright, so let's get started improving this. We will go in the order indicated, so from 1 to 5. First, if T is of finite rank, then, and this is what I explained in words in the last video, this is going to be a bounded thing because T is bounded linear map, so it maps bounded things to bounded things. And if you close it up, so this is a bounded and closed subset of a finite dimensional space, because this is of course in the range, and that range is finite dimensional if T is a finite rank. So you have a bounded and closed set in a finite dimensional space. That thing has to be compact. This was part of the equivalent norm theorem early on. In a finite dimensional space, hence compact. Okay, this already concludes the first part. Now, next part in 2, this is about the norm-closed subspace. There's more than that, right? So there's two statements. When I was discussing part 2, I only focused on the norm-closed part, but of course we also have to show that it's a subspace, right? So if you take two compact operators, take a linear combination thereof, then that thing will still be compact. That's the easy part. The norm-closed part is a little bit harder. So let's start then in 2. Let ST be compact from X to Y and alpha beta scalars if Xn is bounded, an arbitrary bounded sequence, compactness of S. Remember, S being a compact thing, it maps bounded things into sequentially compact things. So compactness of S yields existence of a, bounded subsequence, because it's a subsequence of the initial sequence which was already bounded, so that subsequence is also bounded. Call it X and K, such that the image of that sequence is convergent. Right, so that S, X, and K, K1 to infinity, converges. That's the sequential compactness. Yeah, but then moving one step further, but by compactness of T, we can pick a further again bounded subsequence. Now I have to write triple indices, say x, n, k sub m. This is a subsequence of the previous subsequence, x, n, k, such that the image under T, x, n, k, m is the running index, this is a sequence in Y, converges. Right? This is again the sequential compactness, but now on the level of the image of T. Together, if you look at alpha S x n k m plus beta T x n k m, and you trace out the m, that's going to be a sequence in Y. This thing is a convergent subsequence of alpha sxn plus beta txn and 1 infinity. So that means by definition of compactness, this combination alpha s plus beta t is again compact. Right? Good, because we started with an arbitrary bounded sequence. This was our xn. Where is it? At the very beginning. Xn be bounded. Okay, and then what we just showed is this image sequence of the linear combination of these two guys has a subsequence, this one, which is convergent, and hence that combination by definition of compact linear transformations is compact. All right, so now we know already that this com xy is a subspace. All right, so now to show that it is closed, what we will do is we will take an element in the closure and show that it is actually, well, in com xy, right? So, and then the closure is equal to com xy itself, hence it has to be closed. That's the logic, all right? So if something is in the closure, then of course you can approximate it fairly well with something, well, inside. So for any given epsilon, there exists S in com xy. Right? Because after all, com xy is dense in the closure, right? So trivially, so there exists S com xy, so that you can get close to that initial t less than epsilon over 2, right? It's a norm closed. The norm closed here means, of course, the in-operator norm, all right? But since S is compact, this guy here is totally bounded. By definition, it would be the closure of this guy being, well, compact. Okay, so that means in particular the thing without the closure is compact, hence totally bounded. Right, totally boundedness means you can cover it with finitely many disks of arbitrary small radius. So let's write this out. So there are finitely many y1. So you see it in this case right now, I'm sort of interchanging the two different characterizations of compact linear transformations. Up there we did the argument of the sequential compactness of the image. Now what I'm doing here is I'm going back to our very first definition and playing around with the images of those unit balls, right? So there are finitely many y, so that, well, this is the definition of totally bounded. You can cover it by finitely many balls of small radius. So for instance, finitely many, and the centers of those balls are precisely those yj's. Y minus yj, this is in y space less than epsilon over 2. That's just the definition of being totally bounded. Okay, apart from the triangle inequality, from the triangle inequality, I claim Tx of y is at most epsilon over 2 plus Sxy. Why is this? Well, because maybe in yellow on top. So we have this. This is because of the density. Then this here down there, I should say for which x, for any x in B10, right? So that's why you have a lower bound in the form s minus t x. This would be in y space. This lower bound there is true for all x here in the unit ball. Right, but now you use the lower end triangle inequality, right? Not the upper one. So then you would have, let me think which way I want it. I want it like this: tx of y minus sx of y. Right, so you have this. And then all that you do is you read this one on the far left and this one on the far right, and you bring this little term here with the sxy to the other side, and you get immediately what's written there. Okay, so you have this for any x in the ball, thus, oh, not in yellow, in blue, thus the image TB10 is covered. Yeah, well, so I know already that this guy, the s-axis, are covered by those finitely many balls of radius epsilon over 2, and now here's just another shift of epsilon over 2, so they will still be covered by exactly the same balls, but the radius has doubled, right? Thus is covered by this union, J1M, y in y, y minus yj in y, and now the radius has doubled, as I just said, is covered by this. Hence it is, because epsilon is arbitrary, totally bounded, and hence totally bounded. Totally bounded, right? And remember, this is equivalent to the statement that T is compact. This shows T is compact, and that's why we are done, right? Because what I just did is I took an element in the closure and I showed that this is actually in here, right? But the other implication is trivial, so this must actually be an equality here. So that's why it's a norm-closed subspace. Okay, good. So we're done with this. Now comes this ideal thing. So if you hit it from left and right with bounded things, bounded linear things, then you're still gonna not leave that subspace there. So moving ahead, this is now the third property. If we are again gonna play around with sequences rather than balls that cover the images. So if xn is bounded, okay, then txn is bounded. So in the third case, the t is the bounded one, the s is the compact one. So, but the bounded one maps bounded things to bounded things that we learned in the very first week. Then is bounded for all, well, bounded linear transformations, x from x to y. That's clear, right? Hence, compactness of S implies existence, because that txn will be acting on S, implies existence of a subsequence, call it txnk, k the running index, this is a subsequence of the txn, alright, such that S txnk, k1 infinity, which is, well, by construction a subsequence of this guy here, is convergent. So this composition S circle T is compact. Alright, good. Now we have to do it the other way around. Moreover, if S is compact, and now you hit it from the left with something bounded, how to argue then? Well, then first, then we can select a convergent subsequence S, X, and K, K1 infinity. So remember, X sub n, this is an arbitrary bounded sequence. And since for any t from L, Y, Z, we have the following estimate: Ts X n K minus Ts X n M. This would be in Z space. Typical estimate, you can write this as Ts X n K minus S X n M, and then you do the standard trick again, and then you have Sx n K minus Sx n M. This is now in Y space. Yeah, but this guy here, this becomes small because X and K is a convergent subsequence. So as K and M go to infinity, this will go to 0, and hence the left-hand side has to go to 0, right? Since for any this holds true, we see that T, S, X, and K. Well, this would first show it's the Cauchy sequence, but we are working in Banach spaces, so they are convergent, right? K1 infinity in T, S, X, N, and 1 infinity is convergent. In C. Excellent. Thus, also this composition Ts, where the compact one is on the left and the bounded one on the compact one on the right and the bounded one on the left is compact. Okay. So now what remains now is that last part, which is known as Schauder's theorem, and that is more challenging. So the statement about if you have a compact linear transformation between two Banach spaces, then that happens precisely when the dual transformation between the dual spaces is also compact. It is more challenging because it needs a result that is covered in the metric space module, and this is the Arzelà-Ascoli theorem. So we will be playing around now with function families which are equicontinuous, right? So the equicontinuity kicks in when you're not just looking at one function and ask yourself, is it continuous somewhere, but a whole family of functions. And equicontinuous, that's why the word equi there simply means that your deltas that you use in the proof of continuity do not depend on the member of the family that you play around with, right? And Arzelà-Ascoli theorem is an important theorem because if you have uniformly bounded equicontinuous family of functions, it implies existence of certain convergent subsequences, and that's why it shouldn't be a surprise that this will enter now, because here, when we have to show that something is compact, we have to show that certain subsequences in the image are convergent. All right, so let's get started. So finally, well, it's an if and only if statement, so there will be two directions. So first we pick linear functional on y star. So we will start with the direction t compact. Now I have to show that the dual transformation is compact. So now I have to select something bounded in the dual space of y. That's why I start like this, right? So I have to take a sequence, a bounded sequence in the dual space of y, and show then that the image sequence under the dual transformation has convergent subsequence. And that will be done by using Arzelà-Ascoli theorem. Okay. So finally, if this is true, then if this is chosen, then on the compact metric space, remember I said I assume that T is compact linear transformation, TB1, and that simply means that this is a compact subset, but it's itself a metric space, right? Just this is a closed subset of Y, so it is certainly a metric space. Complete, actually, right? So then on the compact metric space like this, we have that, okay, let's trivial estimate. So f of y is less than operator norm of y. And so if f is from my family up there, then this is less than or equal to the norm of y for all y in, anywhere in the Y space, so in particular in this set. Okay, we have that this, and so the following important thing holds true: f of y1 minus f of y2 is at most equal to, these are linear, so you just bring them under 1f, so f of y1 minus y2, and then you apply that thing that we just had up there, so it is equal to this. Okay, and this holds true for all y in tb1 0 and f in the dual space of that thing with operator norm not exceeding 1. Okay, sort of a trivial estimate, but now comes the punchline. So how do I jump to Ascoli? Well, here's my function family now. Curly f. Those are all continuous linear functions on this. Remember, in Ascoli theorem, you have to have families of functions that act on the real line compact intervals. Right? So that's why also here I have to start with something compact, and that will be precisely the image of the unit ball under the map T. Okay, let's move this here, here. Okay, and now maybe the whole thing, over here. All right, so this family, so these are continuous linear functionals on that compact metric space, which is the closure of the image of the unit ball. And I want this to be uniformly bounded, so I assume this thing, right? So then is a family of, okay, uniformly bounded, that's clear, because all these guys in operator norm are bounded by 1. And how do I see that these are equicontinuous? Equicontinuous. Oh, that's a hard word to spell. Equicontinuous. Well, this is precisely this estimate. All right, this estimate asserts actually Lipschitz continuity, because here is the Lipschitz constant is equal to 1, and it's completely independent of the member of the family f, right? For any member of this family, this one holds true. Okay, so it's a uniformly bounded equicontinuous, is a family of uniformly bounded equicontinuous functions on a compact space, namely the closure of the image of the unit ball under T, right? Ascoli. If you don't remember this one, have a look in your metric space module, or equivalently in the first section of our lecture notes. I reviewed it there. We will need it again later on. Hence, by Ascoli, given any sequence in Fn, but this is by construction then a bounded sequence, there exists convergent subsequence Fn sub k, k1, which converges in operator norm on the space that I consider them. So that is TB1 image and then closure thereof. But now I claim this you can immediately translate into the right statement for the dual transformation. And why is this? Because you have ftx is, by definition of the dual, is equal to this. All right. So I claim that the dual acting on f and k, k1 infinity, is convergent in norm on B1 star. All right, so maybe a little comment about this. So you have good control over f and k acting on tx, right? So maybe f and m. It's convergent, so this certainly is going to be Cauchy. This is the ordinary absolute value or complex modulus. And now you have, by definition of the dual transformation, f and k, yeah, let's write it like this, right from the get-go, fnm x, like this. And now, of course, you do the similar, or always the same trick. Well, yeah, okay. No, I don't wanna, I wanna switch the order of these two things, because I have control over the left, not yet over the right, so it's a bad thing how I wrote it. Well, it's an equality, it doesn't matter how you write it, but for the purpose of my argument, I want it this way, right? So this, and now you can still do the same trick that I was just indicating, fnk minus fnm tx, that you estimate by the operator norm, fnk, fnm, and then, well, t of x, y, right? But remember, x is on the closed unit ball, and this is going to be bounded here. This is going to be bounded, and it's independent of the large variables to begin with, right? So when k and m go to infinity, you have excellent control over the right-hand side. Hence, you have control over the left-hand side, and this for any x in the closed unit ball, right? So now what you do is you optimize over the x. You will generate the operator norm on the left of the dual transformation acting on fnk, and then the statement says, well, that's a Cauchy sequence, but it's a Cauchy sequence in a complete space, so it is convergent, right? And that's precisely what I wrote up here. So the dual transformation acting on fnk is convergent in operator norm on B10. Okay, so this is true. Good. Given that is, so now that we have this is convergent on this, given that, well, I already said this here in words, I already said this is true in the operator norm, so but in my notes I write a few more lines. Given that you have f, the operator norm is supremum x1 f of x, we conclude that TTFNK K1 infinity in the dual space of X is convergent in the norm of X. So this is precisely what I said in words with my yellow writing, now written in the blue color. Okay, so by definition, or this first proposition, the dual transformation is compact linear transformation from the dual space of Y to the dual space of X. Okay, I still have to do the converse statement. I will do this early on in the next video, and then we'll move ahead and discuss our first non-trivial example of compact linear transformations. See you then.